analyze how the numbers are related to each other. Rather than just looking at a T and being, this tells me if it's significant. Actually being able to say, oh, this evaluates the coefficient relative to standard error or how off the coefficient is. Interpretation is one. Second thing is storytelling. If you're a details, you can get focused on interpretation that you actually don't build the muscle of what the hell happened in your research. And actually, at the end of the day, that's more important than the interpretation. The interpretation is what allows you to tell the story, but the ultimate goal is to be able to tell the story of what happened. And both of those just take skill. And they take much practice is because the storytelling changes every time the output changes. It's not you can practice once and then you've got storytelling, because if all the predictors are significant, the storytelling is really easy. All these things contribute to this thing. But when predictors change, when they become significant or lose significance, when you build new models, the storytelling gets more complicated. And the only way to get good at that is to practice. Those are your two really big priorities as you go into the midterm: interpretation and storytelling. Okay. I've said this, this is Quinn's motto, but when you are writing up your APA results, write them up without your stats first as he walks by. Perfect timing. Did you hear your name? Write them up without your stats. Write the story of what happened. You're telling who doesn't know stats, and then just put in the stats to support it. The stats are your evidence for your story. If you tell your story and it just says prove it, and your stats are the prove it. Okay. How much variance and anxiety can be explained by peer pressure? Where do we look? Wow, that was such a wah-wah. Let me try again. Right? Redo. How much variance and anxiety can be explained by peer pressure? Where do we look? Good. Correlation table. Anxiety and peer pressure. Remember that when we're talking about correlation, we're talking about what? Covariance. How these two variables move together relative to how they move on their own. You have anxiety, and then you have peer pressure. You have this variance from anxiety, and then you have this variance from peer pressure. But you don't want to know their covariance. You want to only know how much variance in one is explained by the others. What do you need to do to that 0.45? What is it? What is it?
0.20.
0.2025. You can either say 20% or 20.25%. Anybody know that my handwriting is a lot nicer today? Anybody notice that? No, you didn't notice. Thank you. I have really nice handwriting, but the stylus tip on Apple Pencil sucks. Thanks to Sean. Now I have a cool new stylus tip that's a pen, and I'm very excited about it. It's the little thing. How much unique variance, notice the word unique, in anxiety can be explained by peer pressure in model 2. Now where do we look?
A model parameter.
Good. Which one?
Model 2 model parameter. The bottom.
Model 2. Yep. Good. These are all parameters. Well, not really. These are parameters. These are parameters. These are parameters. And these are parameters. Anything we're estimating about the population is a parameter. Which specific parameter are we looking at?
Beta.
The beta for peer pressure in model 2. Good. Here it is. Again, though, that's our standardized slope, our relationship between peer pressure and anxiety, considering parental warmth, self-esteem, and media. If we want to know the unique variance that's contributed by peer pressure, we once again have to square it. That one more 0. I can do math, I swear. Great. It's 0.06%.
Technically, since it's not significant, would you say done?
Good question. No, you would still interpret in this model. This is still the amount of variance in our outcome that's being explained by uniquely being explained by our predictor in this data set. But M is raising a really good point that I want to make sure is super clear. Is there a relationship between peer pressure and anxiety in this data set? And if so, what is it? Let me say that again. Is there a relationship? Actually, I'm going to broaden out that question. This is really important. Is there a relationship between peer pressure and anxiety according to model 2? Be very careful. Think about that carefully. Wait, think. I want everyone to think. You're going to look. Here's where you're looking. Is there a relationship between peer pressure and anxiety? Sean, you were going to say.
Not a significant one,
Good. Tell me a little bit more about what you mean by that. Why didn't you just say no?
because.
I saw the hands. It was this, but I saw.
Well, it's when it's measured with with self-esteem, the and parental.
Good.
It's not significant because it's over 20.
Why else, Hannah?
Because it is only that when the others are taken into consideration.
No, Lily. No, Kayla.
Well, I think, when we're saying, because they all getting together, but when it's in this model, it's not.
Getting closer. The answer lies in the type of statistics that we're doing. What type of stats are we doing? Inferential statistics. What does the P belong to? It's a hypothesis test. What's a hypothesis test for? Hold on, what's a hypothesis test for?
Inferring.
Inferring about what? The population. What's that 0.08? No, for this data set. Using the data points that we have in this data set, the best estimate is a slope of 0.08. That's a slope. It's not 0. But we don't care about the slope in this data set. That's not what we're interested in. We're interested in whether peer pressure predicts anxiety in the world. And what we're doing is we're testing whether that beta of 0.08, is it significantly different than what? Than 0. That's the null hypothesis in that t-test. This is what we got, and the null in this t-test is beta or b equals 0. And in this case, what it found was that your slope of 0.08 is not significantly different than 0. No, there is no relationship from a storytelling perspective. There's no relationship between peer pressure and anxiety when you consider these other 3 things out there in the population. But when you interpret that beta in this data set, you're not going to be like, when you move over 1, you go up nothing. When you go up by 1 standard deviation, you go up by 0.08 standard deviations. It's part of the equation. It's not 0 in the equation. In this model, it's not 0. This model is based on the data. Does that make sense? That's really important to distinguish. I think we lose sight when we see p-values in T because we haven't done hypothesis testing by hand for a while, that we're always deriving because we have normal data. That's the point of, that's the entire mechanism of parametric or normal statistics, is that because our data are normal-ish enough, we are making inferences about the population from sample data. This is the best estimate of the population because it's the best fit for our sample. And we're considering our sample representative of the population. And then we're adding an inference test on top of that, a null hypothesis test, to test whether that regression coefficient is significant out there in the population. And the way we test that is we say, this is the best rule we've got, but then we test it against what? But how do we get that test statistic? How do we get T?
Standard error.
B over standard error. So this is the rule, and then this is how much people deviate from that rule. How bad that rule is, basically. Good. I digress, but importantly. Interpret the beta for parental warmth in model 1. We're looking here. Remember, you want to get as in context as you can. So let's go back here. Let's go back here and see parental warmth is the degree of emotional support. Let's assume that's measured on a scale. Interpret parental warmth for me. Quickly, we don't have time. We got a whole new thing to cover. Go.
For every one standardized unit increase in parental warmth, we expect a 0.29 standardized unit decrease in anxiety when considering.
Perfect. Good questions about that. When considering for, when accounting for, whatever, either is fine. Good. Interpret the unstandardized regression coefficient for media in model 2. Now, here's an important one. How is media used or measured? Hours. Are we gonna say for a 1 unstandardized unit increase in media? No, we know what an unstandardized unit increase is. What is it? 1 more hour. I'm gonna do this one. For every, I'm gonna say the normal sentence frame would be for a 1 unstandardized unit increase in media hours, but I can replace that with the actual unstandardized unit. I can say for every additional hour that a kid spends on media, we can expect their anxiety score to go up by 0.24. Much more contextualized. And now we're not at recall. I'm now at apply. And most importantly, tell the story of what you found. Quick, you just did it for 10 minutes. We have a whole new topic. You don't want to do the DA without the demo, I promise. Online. Thank you so much for volunteering.
I can take a shot. In model 1, we found that.
Pause. Rather than telling me chronologically what you did and what you found, I'm the high school guidance counselor. I don't care what models you ran. I don't care about regression coefficients. I just want to know. You're writing an article for me or you're writing a report for me. What did you find? Take the I ran a bunch of regression stuff out of it.
Can I say when we consider just these 2 variables versus the 4? When we were just looking at parental warmth and peer pressure, we found that the more parental warmth a student had in their life, the less anxiety they had, and the higher levels of peer pressure that they experienced, the higher levels of anxiety that they would have. They're predicted to have higher levels of anxiety. And then when we added self-esteem and media to that, we found that parental warmth was still really important for predicting anxiety with maintaining the same relationship, that more parental warmth is less anxiety. Peer pressure still maintained that same strength in the relationship, but it's not as significant anymore. It's not deemed as important because we've added self-esteem and media to consider. And we found that the higher the self-esteem of the less predicted anxiety they were to have. And then the more hours of media use they were to have, the higher levels of anxiety they were predicted to have.
Good. 100% statistically accurate, but long, which is 100% natural as you're developing your storytelling ability. So when you're telling your stories, the way you know you're getting better at storytelling is they get shorter. 100%. But when you're really good at storytelling, you can tell the story of what you found in a sentence or 2. Now, what would you change or add to AJ's start? You don't need to actually do it, but how could we take that as a base, which was 100% correct in terms of interpretation, and take it to the next level? He had a big chunk of in there that we don't need in there. What was it? No, he didn't say any stats. What was it? Huge chunk.
First model.
The first model. What did we learn statistically? Model 1 explained 43% of the variance. Model 2 explained 58%, and the difference was significant. Remember that these variables are all operating out there in the world on their own without our influence. These are just 2 windows into them. Window 1 or model 1 was a partial window into 2 of them. Model 2 was a better window into them. We don't need to talk about model 1 because it's not we learned from model 1 that model 2 doesn't tell us. Model 1 doesn't, if we look at model 1 and we talk about it, if we look at model 1, it doesn't mean that self-esteem and media aren't out there playing a role. That's really important. They're still happening. We just aren't measuring them. But model 2 was a better model. When we're telling the high level story of what happened, that's not necessary anymore because model 2 was a better, explained more variance in anxiety than our first model. First of all, we can cut all of model 1 and we can go straight to model 2, unless I'm reporting and writing things up for a stats journal. If we're saying model 2, we can say, now we can say, what's the story? Parental warmth, where's my PBS? Parental warmth, self-esteem, and media, or we could even start with peer pressure. Here's how I would start. Peer pressure on its own has a significant relationship with anxiety. It makes kids more anxious. But interestingly, when you consider their parents' warmth, their own self-esteem, and how much they use media, the impact of peer pressure goes away. That's the high level story. That was 1 sentence. 2 sentences.
Hey, Jess, quick question. For the R squared, does it matter that for model 1, the R squared's at parental warmth, and for model 2, it's at the intercept?
Oh no, it's just down 1 line. I would usually put it at the top line, but it doesn't matter.
Gotcha.
Just doing high level. And I can say parental warmth. Yes, I could be much more specific and say parental warmth makes anxiety go down. But if I'm sharing what I just said, those 2 sentences, are you left going, gosh, I really wonder what parental warmth does to anxiety. Does it make it go up or down? No. If I say to you, hey, peer pressure makes kids more anxious. But it turns out when we consider how warm their parents are, how much they use media, and their own self-esteem, peer pressure doesn't matter anymore. Does that give you a complete picture of what happened? I might add on the end of all of those. Turns out parental warmth is the most important, but that's all I need. There's a question.
Is it in the longer results, right, outside of the high level, like 2 sentence thing? Would you include your parameters from model 1?
Yes.
Yeah, okay.
Yes. Well, good question. In a longer write-up, if I were running a series of models, I would always include, this is important because I got a lot of questions about what to include in DAs, which is really what do I include in a manuscript? When it comes to model coefficients, the things you see in this table, you do not want to run anything and talk about it. This is the rule. You don't talk about anything and leave the reader wondering what that model looks like. That's the bottom rule. That's the bottom line. Don't leave the reader wondering. How you decide to satisfy that reader's curiosity is flexible. Do you write all of those betas for the model you don't choose in narrative? I wouldn't, right? I would be, my first model regressed anxiety on parental warmth and peer pressure. That model explained 43% of the variance in anxiety, R squared equals 0.3. See table 1 for regression coefficients, period. My second model added in media and self-esteem. This model explains significantly more variance than model 1, delta R squared P. Then whatever my final model is, when I want to actually talk about my predictors and what I found, when I want to tell the story, then I might use the betas in the narrative. But betas for models, I don't want to talk about. I just want to say that I ran. I'm never going to put them in the narrative. I'm always going to put them in the table. Does that help?
If model 2 hadn't been significant, do you still want to unpack that in your story at the end?
If it hadn't explained more variance. If it hadn't explained more variance, that would have meant that both media and self-esteem had to be not significant. Because if the whole thing, if adding both of those 2 things, salt and pepper, if both of those didn't make it better, then neither of those are good. In which case, that together is the story. Because then I ran the first one, then I ran the second one. Weirdly, those 2 things don't make it better. Turns out you only need parental warmth and peer pressure. You don't need self-esteem and media. The betas from the first model become the betas you'll use, but you can't tell it without telling that these 2 aren't significant. That's the challenge, is now that we're in model building, there's no more recipe for your DA. A lot of you are, do I do this? Do I do that? Do I do this? I can't. Now your own decision-making has to come in your DAs, because you're going to be in DAs where you run 4 models. and you're gonna report, I don't know, 2 of them. And then you're gonna, and if you're approaching DAs, copy, paste, do adjusted, it's not gonna work. Because you're gonna get a result and your instinct should be, I still have a question. Now I'm gonna run a new model. But you're gonna have to come up with that model, because it's not gonna be the one I ran in the demo, because the research is different. That kicks in hard in regression. The decision making, you can't robot your way through regression at all. In fact, once we get past next week model building, your DAs are gonna start looking different from each other, because you might opt to run different models than you might opt to run. That's the research and decision making part. Because that's what happens in the real world. Nobody's run these 4 models and don't think. Bummer. Cool? Oh, that was way longer than I planned to spend on that, but it's good, good. Learning is good. Stats humor, I love this one. Conviction, knowledge, I'm not full of shit. It's a good one. Arrogant on insecure zone, humility sweet spot. We can all self-diagnose where we are on this graph. Accurately, I don't know, but we can all self-diagnose. Regression for smarties, multiple regression with categorical variables. Couple announcements. Today is this panel. I'm assuming that's what these chairs are for, even though we did, but instead of just continuous predictors, we're mixing continuous and categorical. Cool? That's it. We got to fly a little today. All right, how do we build a model within the general linear model using categorical variables? Again, goal here is the same thing, interpretation and storytelling. That's it. The one added pieces, in order to be able to use categorical variables, you have to be able to procedurally manipulate them into the general linear model. Chloe, this one's for you and your data set. We're gonna go straight into an example because you have a foundation of multiple regression already. This one is an example I wrote last year, and now it's really depressing. A political scientist is interested in what predicts an individual to vote. Past research demonstrates that age, voting history, and trust in government are all significant predictors. She's convinced that U.S. party affiliation, Democrat, Republican, Independent, we're keeping it simple, plays a role in the vote, and she wants to test this hypothesis. So she's got to vote, age, voting history, that's percent of elections voted in since the age of eligibility, that's continuous. Trust in government is a Likert scale, and then party affiliation is categorical. Democrat, Republican, or Independent. So she's got a mix, here's her data set. She's got a mix of continuous and categorical data. If she only had party affiliation, what could she, you know what this means? Jess and AJ, get ready. You'll have to ask them. I can't talk about it out loud, I'm recording. That means they have to do that. Party affiliation. If we only had party affiliation, if we wanted to predict a vote from party affiliation, Democrat, Independent, Republican, what would we run? What kind?
It's a variance.
One way between group ANOVA. But now we have categorical, and we want to combine it into a model with these continuous stuff. The problem is ANOVA cannot take continuous variables that are of interest to us. Yes, we can run an ANCOVA that controls for a covariate, but that's not what these are not covariates. We don't want them to function controls. These are actual predictors we're interested in. We want to use the general linear model, but a reminder that the general linear model is a linear combination, and under the GLM, every variable, voting history, age, trust in government, party affiliation, is multiplied by a regression coefficient, a weight, B or beta, to determine how much it contributes to the model. Well, how do we multiply a word by a weight? You can't. You can't do B, let's say the coefficient is 0.15, 0.15 times independent. I don't know how to do that. We have to figure out a way to get this party affiliation variable into a numerical form that we can multiply by a coefficient in order to put it into a regression coefficient. Here's one model she could run. To vote equals age plus voting history plus trust in government. If we wanted to write this equation, we could write y equals b sub naught, there's our intercept, plus b1 age plus b2 voting history plus B3 trust. No problem. All numbers. What about if she wants to add in party affiliation? Well, now that's our fourth variable. If I want to write this one, I have y equals b sub 0 plus b1 x1. I'm just using x's now, but it's the same. b2 x2 plus b3 x3 plus b4 x4. Herein lies the problem. We all see the problem? Everybody online see the problem? Now we're going to learn how to use that problem. Here's our data set. The question is, how do we turn party into a numerical code that would allow us to use it in the regression equation? What is one idea you have for how to do that? If you know how to do it correctly, you are not allowed to answer this question. What's your instinct? What's our usual instinct when we do things?
Whichever party you best gets a higher weight.
I love it. That would be 1, 2, 3. Cool. I purposely did not do that my affiliation would not be evident, though I think it's pretty written on my sleeve. Good. That would be one option.
Is percentage of how many?
No, hold on. This would be one option. Okay, we could just do 1, 2, 3. What's the problem with that? I'm gonna tell you now, that doesn't work. Don't do that. Why? Because when you graph it, if you were to graph the relationship between party and the vote, this is what it would look. Oh my gosh, I don't know what that is. I hope it's not school. I really hope it's not school. This is what it would look. Is an independent actually higher? Not numerically. Is the value higher than a Republican or a Democrat? No, they're categorical. They're ordinal. They're not, they're nominal. There's no order to them. We can't give them that number values that actually signal order. 1, 2, 3. Because that actually means that you are getting higher in the value when you move from one to another versus ordering them independent Republican, Democrat is no different, but it would produce a very different result in the coefficient. Does that make sense? They're just categories. We are not going to do this. Got it? Big no-no. What's the other option? The other option that you see a lot are 0s and 1s. 1 to indicate yes, 0 to indicate no. When we do it for all three, it's called full dummy coding. We have a column for Democrat, a column for Republican. Spoiler alert, we don't do this either. When we have a column for Democrat, column for Republican, and column for independent, then we code each one as present or absent. The Democrat, we give them a 1. If they're not, we give them a 0. The problem with this method is multicollinearity. As you know, 2 of the variables, you always know the other one, okay? As you know 2 of the variables, the other one is 100% predicted. We don't do this either, got it? Want to know what we do? All right, what we do is what's called dummy coding. Not full dummy coding, just dummy coding.
Would your category only have 2 options?
No, well,
Like, if you didn't have an-
no, you'll see what we do. Dummy coding works when you have 2 options. What we're gonna do is dummy coding. We're still gonna use 0 and 1 to indicate the absence or presence of a categorical value, but we're going to choose one of the levels to serve as the reference group. What that means is one of the levels is going to be the group to which we compare the other 2. Let me show you how this works. Here's our data. I'm going to choose Democrat as the reference group. My choice to choose Democrat as the reference group in this example is totally random. To choose a certain level as a reference group, and I'll give you examples in a second. But for now, we're going to go with the reference group is random. One of the levels, it doesn't matter. That means we're going to create 2 dummy coded variables. The first dummy coded variable is the difference between our reference group and Republican. And the second dummy coded variable is the difference between our reference group and independent. However many levels you have of your categorical variable, you will always have one fewer dummy coded variables. If your categorical variable has 2 levels, white POC, how many dummy codes are you gonna have? 1. If your categorical variable has 5 levels, how many dummy coded variables do you have to create? 4. You'll always have one fewer because one of those levels is serving as the reference group. What we do is the reference group is Democrat. Now we look, this is a Democrat, that's first. Are they a Republican? No, they get a 0. Are they an independent? No, they get a 0. Next, an independent. Are they a Republican? No. Are they an independent? Yes. Next, a Democrat, 0, 0. Next, a Republican, 1, 0. You see the scheme? If you are the reference group, you have 0, 0 across all dummy coded variables. That doesn't mean nothing. It means you are the reference group. That's an important switch. Usually a 0 means absence of. In dummy coding, all zeros means the reference group. It's a really important concept. Then you have 1 or 0 in your other 2 dummy codes to represent your other 2 levels. Now, first important concept, all zeros in your dummy codes represents the reference group. Second key point, I usually name them D1. I usually actually name them D1.rep for Republican and D1.ind for independent, so I don't forget. Otherwise, I'm what the hell was D1 and D2? I don't remember. Second key point, these 2 variables, notice it's 2 separate columns in my data set. It's going to be 2 separate terms in my regression equation, but they together represent political party. Key point number 2, you cannot, under any circumstance, divorce or separate dummy codes. Meaning, one of these variables is not political party. Political party has 3 levels. To fully represent all 3 of those levels numerically, you need both of these variables. You will never put just D1 in your model or just D2. They cannot ever, ever, ever be separated because they are only collectively political party. Does that make sense? Questions about that?
Can't you not add the beta of something?
You cannot do anything. They are separate, completely separate. No, you can't add the beta.
I mean, like, for multiple regression, but then they show up as 2 variables.
Yes, they are 2 separate variables.
But if you want to see the.
You can't.
Oh, you just can't.
Nope. If you want to see the percent of variance explained, we're gonna get there in a second. But there are limitations to dummy coding categorical variables.
0, 0, 0, 1, 0, how that makes it continuous versus categorical, because I feel like I'm just I'm just seeing 0, 0 instead.
Well, go back to this, actually, give me 2 slides and you'll see. Key idea, 2 key ideas, they're here. If you have 3 levels of a categorical variable, you need to create 2 continuous dummy coded variables. It's the number of levels minus 1, always. Second key idea, your categorical variables are fully represented by all the dummy codes together. They can never be separated.
Hey, Jess,
Yep.
are there ever, I can't think of an example, but are there ever scenarios where you would have a 1-1 entry?
No,
Where
never.
No.
No. Nope. Every column, that's the point, that's the idea of that's why they all go together. Across, think about them, even though they represent 2 separate variables in your regression equation, you should think about the 2 of them together as political party. If you had a 1 and more than 1, it would mean you are more than 1 party. And we know from our categorical variable, you can't be more than 1 party. Let's look at the 3 models that we're gonna run, and this will answer your question, Bren. Model 1, we're just gonna look at a simple regression, predicting to vote from voting history. Model 2, we're gonna predict to vote from voting history and party affiliation. This is gonna get to your question. And model three is gonna predict the vote from voting history, party affiliation, age, and trust in government. Throw it all in there. Here's the first one. We've got predicted voting, predicted by voting history. B sub 0 is our expected to vote when all predictors are 0. You want to practice? Here's a good take yourself from recall to application. When you are interpreting your intercept, don't say that. Don't say that. What should I say instead if I want to take myself from recall to application? Amelia, this one's for you. What do you want? What do you say? What do you say if we take it from recall to application instead of this? Instead of this is the expected of Y, or even just this is the expected to vote when all predictors are 0. What would you say instead?
It's the vote, if they have no voting history.
Or even more, that's still just repeating that a little bit. There we go. Beautiful. This is the expected, this is how it is to vote when they are a first-time voter. Or this is how it is to vote when they've never voted before. That's what it looks to take it to application. Don't read the variable name. Think about what that variable is measuring and how you would actually talk about it if you were talking about your research. Start practicing that. Don't robot it. No more robots. Good. Here's our first model. Now, getting at Bren's question, Bren, what are we going to put in here in that X? Just their voting history. If we go back to the data, we're going to put that number. Good. Easy. It's a number in our data set. Now, second one, we've got predicted voting, and we've got expected to vote when all predictors are 0. If we want to contextualize that, it's predicted to vote when all predictors are 0. Let's do that. What does it mean for voting history to be 0? First time voter. Good. Now we've added in political party. But remember, political party are now our two continuous. Can you plug a 0 or a 1 in? Sure, they're numbers. That's what makes it continuous. Can't plug in the word independent or Democrat, but I can plug in 0s and 1s. They're very simple. What happens if you plug in a 0? It goes away, and that's going to become important. Here's a question. What does it mean? This is why you can't just get, this is why you can't say when all predictors are 0. If I plug in a 0 and a 0 here, that means, what does it mean? You're who? You're the reference group, which in this case is the Democrat. Now, put that in context. Good. That's your predicted voting for a first-time Democrat. You're as minus 1. Yeah, good. Right. Here we have our model fit, and this is going to answer your question. You're like, but what if I just wanted to know variance explained by voting? Well, add it together at one time. Here you go. Here's model 1. It explains 12% of the variance. What did we add? What was the SALT from model 1 to model 2? Party affiliation. Can I add D1 first and then D2? No! What's the rule? They can never be apart. Party affiliation has to go together. I can't add D1 in a model and then in the next model add D2. They have to be added together. They're one. Think about it this way. Here's a good way of thinking about it. This phrase might help. One construct, two variables. Does that help? One construct, political party, measured by two dummy coded variables. It's one construct. You can't separate it. It's taking the word political party and being, this one's political and this one's party. Can't do that. Political party.
Just to clarify, in the regression equation itself, could you switch which order?
Oh, that's just linear. I just meant in model building, they always go together. What's the only thing we added between model 1 and model 2? Party affiliation. Ask the question, well, what if I want to know how much variance in the vote is explained by party affiliation? How do I tell?
Your delta?
Delta R squared. Because what's the only thing I added? Party affiliation. Any increase in variance explained is because of the SALT. Because of the party affiliation. Party affiliation explains how much variance above and beyond. 19% more variance above and beyond voting history. Good.
And this value will be the same if, let's just say, for both models, you added age. It will also be the exact same.
Not necessarily.
If you, for model one, if you added voting history and age, for model two, you have voting history, party affiliation and age. Well,
Not
that's,
necessarily,
not-
because it depends on how they're correlated with each other.
Wait, then, that means that the variance.
Hold on this, hold on. If you really just wanted to know party affiliation
Yeah.
and how much variance was explained, what should you do?
Oh, let it run.
Run an ANOVA and get the ADA. But I'm gonna show you that in a second.
Oh.
Okay, let's dig into model two. Here's the model. We've got y equals, here's our intercept. Here's B1 times voting history. And then here are our dummy coded variables. Here's our regression coefficients. I'm gonna add the Republican and independent, just so we don't forget that we made Democrat the reference group. Now, the continuous variables are old hat. We know how to interpret those. If we look at history, voting history, for a 1% increase, here's another good regression. That looks super small, doesn't it? But it's significant. And that beta is pretty decent. In fact, it's larger than the next one. Why is that small? The standard error is small, but that doesn't influence the B. That influences your T. Why is that B small, even though the regression, the weight, the beta is clearly.
Measured in percentage.
Say that louder.
It is measured in percentage.
The raw unit is percent. What is one unstandardized unit increase? 1%. It's nothing. So that's saying for a 1% increase in voting history, we'd expect you to be 0.01 more to vote. Here's a fun question. What about a 10% increase in voting history? You can do math. Better than me, in fact. 0.1. That's it. Considering what? There's only one. Considering what? Party affiliation. Good. I'm just getting us more practice with coefficients. You have to consider when you're looking at the B, the number is not, whoa, that's big, whoa, that's small, because they're unstandardized. You have to consider what they're measured in. Now, let's do the new stuff. D1 and D2. I want to interpret D1 for me. Let's first look if they're significant. D1, Republican, is not significant, and D2 is significant. The first question I'm going to ask you, and this is a key point, is party affiliation a significant predictor of the vote?
Yes.
I'm going to ask you, and then the answer is yes or no.
Yes.
The answer is hard yes. And then I'm going to tell you what are two different pieces of evidence. You're going to want to write these down. The answer is yes. And there are two pieces of evidence that you can give me that prove yes. One is gold star evidence and one is silver star evidence. Yes, this comes up all the time. What is the gold star evidence that you can give me? Say that loud. Good. The best evidence to tell me that party affiliation matters is that when you added party affiliation to the model, it explains significantly more variance in the vote. Why is that the gold star? Because we didn't divorce the two dummy codes. We just said, hey, when we added the whole party affiliation in, we did better. That is the best evidence. When I ask you, hey, is this categorical variable significant? Don't give the betas, give the delta R squared. It's better. And if you don't, everyone's gonna say, remember that time Jess stood up here and said, don't give the betas, give the delta R squared? Silver star evidence, still evidence, not as good, but I'll take it, is, what's the rule about demicodes? You can't what? You can't separate them, you can't divorce them. Which means if one of them is significant, party affiliation matters. Just not differences between every level, but there are differences. And we're gonna look at what they are. Let's start with D2. I want to interpret D2 for me in rote language. I have it down here, but I want to do it. Not robot. I'll start you. For every 1 unit raw unit, keep going, increase
Dependence?
I said wrote, in D2, we'd expect a 1.37 decrease or drop in considering voting history.
Hey, Jess,
What? What's up?
can I ask a question with that? If to vote was measured, let's say in percent, instead of saying weird, we'd expect a 1.37 decrease in the voting, which is weird. Could you say, if it's measured in percent, you can say percent?
100%, that'd be
Okay.
much better. A
Yeah.
1.37% drop in the voting, 100%, that'd be
If it
so
was
much
measured,
better.
if it was.
Like I said, if you know what the variables are measured in, which you always will, because they're your variables, rather than saying, when you're talking unstandardized, get the word raw unit or unstandardized unit out of your brain and actually use the unstandardized unit itself. Always. It will always make for a better interpretation.
I don't understand how this interpretation is meaningful.
I'm not done yet. I'm not done yet. What?
Is there, you said in D2 rather than contextualize it with.
I'm not done yet. Hold on. I asked us to start in robot, remember? Hold on. Now. Good. All right. Now I want to highlight part of it. A 1 unit increase in D2. What are the only possible values that D2 can take? 0 or 1? What is a 0? What is a 0, 0? What's the reference group? Democrat. What would a 1 in D2 mean? Good. What does a 1 unit increase mean contextually? The difference from Democrat to independent. When you are interpreting a 1 unit increase in a categorical variable, it is always from the reference group to that level. In D1, what are we comparing for a 1 unit increase? Republicans to Democrats. For a 1 unit when you think about Democrats versus Republicans compared to Democrats, we'd expect a 0.36 decrease in the voting, considering voting history. Now, is there a significant difference in the voting between Democrats and Republicans? No, that's this. Is there a significant difference between Democrats and independents? Yes, that's this.
Hey, Jess.
Hold on. But what's the we're missing? Republican to independent. That's the limitation of dummy coding. Because your research question is not, think about research questions. Your research question is not, I wonder how different party affiliations differ in their vote. If that's your question, great, run an ANOVA. Your research question are, how do these linear combination of things predict the vote? If you're particularly interested in a certain difference, change your reference group. Let me give you an example. When I'm running demographics in regression models, I will almost always make the majority group my reference group, because I want to see whether change from majority group to marginalized identity changes that regression coefficient. If I were doing, let's say I kept all of my racial identity categories, it would make very little sense to use one of my marginalized identity groups. Let's say I use Native American, American Indian, and Alaska Native as my reference group. Then every other group would be comparing to that group. Every regression coefficient would be up to that group, which holistically probably wouldn't tell me what I'm interested in. Versus if I compare every identity to majority white and Caucasian, that will tell me, oh, compared to individuals with majority identity, racial identity, actually, this goes down for Black employees, or this goes up for Asian employees. You have to be thoughtful about what your reference group is going to be, and it doesn't matter.
Jess, if we have a model of just D1 and D2, would the intercept be the reference group?
Yes, yep, we're gonna get to that on the next slide. This gets to what Jeff was just asking, which is what's kind of cool about dummy coding is that when we don't have categorical variables, we only have one single regression equation. But when we have a categorical variable, we can do one extra thing, which is we can make separate regression equations for each group. We can say, hey, for Democrats, this is the equation. Check out how we do that. Here's the final equation, 4.48 plus 0.01 x1 minus 0.36 x2 minus 1.37 x3. And here is just a snapshot of what our data looks like. Let's say that we wanted to find the regression equation just for Democrats. What would I put into this equation to signal Democrats? I would put zeros here and here. This is going to vary. Democrats have different voting histories, but all Democrats will have 0, 0. Oh, that's not what I was doing in this one. I can do that on the next one. This is predicting. If I want to predict this, all we do is plug in their values. It's this one that I wanted to show you. Here we go, Democrats. Here's the equation. All I do is plug zeros in, and what happens to these two terms? They go away. Here's the simplified equation for Democrats, which gets to Jack's observation, which is the intercept of the full equation belongs to who? The reference group. Now, let's do Republicans. What are they going to get in these two open parentheses? 1 and 0. What happens to this term? Here, it goes away. And what happens to this term? It becomes a what? A constant. It becomes negative 0.36. Where's it going to go then? What's it going to change? The intercept. I get y equals 4.12 plus 0.01x. Notice the relationship between voting history and the vote didn't change. Here's independent. What are they going to get? 0, 1. Same thing. This goes away. This becomes a constant. And we get y equals 3.11 plus 0.01. Now, the slope between voting history and the vote didn't change. How do we interpret this? Exactly. How do we interpret this? How do you interpret that kind of coefficient? It's the relationship between x and y considering the other predictors. This 0.01 got determined already considering that those party affiliations would change. That's why it's always the same. You can actually graph these, and this is what it looks like. The relationship between voting history and the voting is the same in this model for Democrats, Republicans, and Independents, but they start in different places. Democrats start more to vote. We don't know. Actually, we do. Hold on. And Republicans and Independents to Republicans. And let's play with this a little bit. What did we learn from the D1 and D2 regression coefficients? Where was there a significant difference and where wasn't there? Whoa, it all comes together. It's crazy. Where was there a difference? Remember, if you go here, remember that we see a significant difference between Democrats and Independents, but no significant difference between Democrats and Republicans. You can visualize that here too. That means that this is significant and this is not. Cool. We've got 3 models. I'm gonna go because we got a demo to do. 3 models. Now we have the 2 we ran, voting history by itself, voting history and party affiliation, which we know explains significantly more variance. Now we're gonna add the other 2, trust and age, on top of it. We already know that model 2 explains significantly more variance in vote than model 1 does. Does model 3 explain significantly more variance in the vote than model 2 does? Yes. Do we know which of the predictors did it? No. Could be trust, could be age, could be both. We don't know. That's one of the downsides of adding variables 2 at a time or 3 at a time. They're still nested because all of model 2 is inside model 1. You don't have to add things 1 at a time, and we don't. But the downside to adding things two at a time is that you don't know from if it's one, the other, or both. But you know at least one of them is significant. Because if neither of them were significant predictors, then what would happen? The R squared, the delta R squared would be not significant. Good. Here it is. Here's everything, the kitchen sink. And let's go straight to where my eyes go. My eyes go here. I'll be honest, I don't really look at the B's. It's important to understand them and to be able to interpret them. But for story, I don't go to interpret first. I go to storytell first. Why? Because I'm rooted in the research question. I want to be able to answer the research question first. Then I get into the nitty gritty. And actually, really how I do it, this is how I actually do it. Even when it's my own research, the very first thing I do is this. I'm to vote. Voting history, Dem to Republican, Dem to Independent, trust, age. That's what I do on a piece of scratch paper. And then the next thing I do is this. History, voting history, point, what?
You activated sorry.
Oh, 0.30, significant. 0.30, check. D1, negative 0.03, not significant. 0.03, nope. D2, negative 0.41, yes. Age, negative 0.44, yes. And trust, 0.15, no. And then I make it really clear. Yep. Oops. We'll make it green. I'll do better. Yes, 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 no, no. And that's what I use to tell the story. I use the picture. When we're predicting to vote, voting history, political party, and age all predict to vote, but trust doesn't when included in the model. If you were going to run one more model, what would you run? One without trust. Exactly. There's a difference. Hold on. There's a difference in the vote between Democrats and independents, but there's no difference in the vote between Democrats and Republicans. Go ahead.
Along that same line of thinking, let's
Mhm.
say you went and ran a Model 4, which dropped trust, and you
Yep.
noted that it explained no more significant variance than what we're showing here. So that's good. We've got a simpler model that's still just as effective. But we all know that independence is the level of the categorical variable that appears to be significant. Could you further reduce the complexity of the model by going back through your dummy coding effort and saying, I'm going to bin the reference as Democrat or Republican, and then
No.
just have a 1 for independent? That's invalid for.
Well, I guess you could, but you're reducing what people's actual political party are. You're choosing parsimony over accuracy of data, which in that case is not a choice I would make.
Okay.
Having a model, it's not your goal is to have a model with no significant predictors over everything else. That's not a goal. That's a goal. It's a goal to not have a predictor in there that doesn't do anything. But in this case, you don't think about these as separate predictors. That's one construct predicting the vote. It is a significant predictor. Party is a significant predictor. It's just that there are differences between certain levels and not between other levels. And it doesn't matter that D1 path is not significant. I wouldn't collapse Democrats and Republicans because Democrats and Republicans aren't the same thing. And knowing that they're not different is valuable information for the model. Yeah.
What?
Hold on. Go ahead, Victor.
You're just trying to determine whether or not party affiliation is significant, not within it. If both those are insignificant, does it make sense to rerun it with a different reference to ensure that third one might create the significance?
No, probably not. If there's no difference between Democrat and Republican and no difference between Democrat and independent, there's no difference between the third, you could rerun it to check. You could visualize it to see if that's before you actually decided to shift the reference group. If it were, it would be a really minor difference. But what I would probably do is, again, the other thing you could do is visualize your data first to see you're going to see the means for each of those groups first. And that might inform what you make the reference group, for example. But you're focusing too much on there being differences between the levels That's a NOVA mindset. Your research question is not anything about the differences in levels. You don't care about that. Postdocs don't matter here. That's not your research question. Your research question is, how do we figure out what will make people vote? And does party affiliation play any role in that? And if how much?
Party affiliation, the most recent added on variable, how do you know how much variance is explaining?
You can add the unique variances of the squared betas. You can get the unique variance of D1 and the unique variance of D2. But it's not a good, it wouldn't be the way that I would recommend it. Because what you don't know, it's gonna share variance with other stuff. The real way to figure out how much variance it explains is either a model with just that in it. That's the best way, honestly. Run a simple regression with just D1 and D2 in it. Yes, that's why. Because it depends on what you want to know. If your question is, how much variance in the vote does political party explain on its own, then run a simple regression. If you want to know how much unique variance political party explains in the context of voting history, age, and trust, square those betas and add them. It's a completely different research question. Speaking of, in the next slide, one other point about dummy coding. Other points about dummy coding. Dummy coding variables are not appropriate for centering. Why? What do we do when we center? We subtract the average. If you can only have zeros and ones, the average is not a meaningful value. We do not center dummy coded variables. We don't put dummy coded variables in our R correlation tables. We leave them out. Why? Because again, this is what you look when they graph them. They don't follow a line. If you try to get a correlation, they're going to look at that. It's going to give you one, but it's not a valuable descriptive stat.
Is there any type of coding where we can?
No, but you'll center the rest of your predictors. Quick clarification. You will still center your continuous predictors in the model. You just will leave the dummy coded ones alone. All right. Now, all of these questions about levels and how do we tell the difference, and a reminder that ANOVA is just a special case of regression. I'm going to show that to you numerically. Not that you don't believe me, but I'm going to prove it to you numerically. Check this out. Here's the model, new model. Employment category, manager, clerical, custodian, predicting previous experience in months. Okay, simple model. You don't know from this picture what we're analyzing it with. If you just got this model, what would you run? I'd probably run an ANOVA, but watch. Let's look above the line to start. Here's an ANOVA. We have our means. We have our F-stat, 69.19. It's significant. We've got our degrees of freedom, 471. We've got our variance in, what was the outcome? Remember? Previous experience. We've got our variance explained in previous experience, which is 23%. Now, check out our simple regression. It's actually a multiple regression. Why is it a multiple regression? Because it's D1 and D2. There's technically, under the hood, there's two predictors. They just make up one construct. Look at what is the same. First of all, look at the variance explained. Same as the ADA. If I run a simple regression or an ADA, this goes to Kayla's question, I'm gonna get the variance explained by just that predictor, that categorical predictor. Check out my F-stat. Why is it the same? Because the model's the same. The statistical technique changed, but the variables didn't, the model didn't. The quality of how well it predicts compared to nothing didn't change. Now, check out the yellow. Here, up top, that's the difference between clerical and manager. There's a difference of 7.42. We have standard error, degrees of freedom, and our T-stat. Look at our coefficient for D1 and all the subsequent stats. Identical. Now look at this one. Identical. We're only missing this because what's the reference group? Manager. Identical stats. Crazy. Yes.
If we make clerical the reference group, we should see.
Yep. If we made clerical the reference group, you would see this one and this one, but not that one. Yep. Whenever you dummy code, you don't get all three, you miss one. And this, by the way, is always, this is talking about a dummy code, a categorical variable with 3 levels. We could be working with 2 levels or 4 levels or 6 levels, but you'll always miss one pairwise from the regression table.
Even though they give you basically the same information, would you say one is better than the other?
No, I mean, it gives you the exact same information.
You get one more. And to know that.
Again, it depends on your research question. If you are wondering about differences between if this is really your model, you want to know whether previous experience differs based on employment category, I would run an ANOVA because you want to know the means. You want to know how much previous experience do each of these 3 have, and you want to know where all the differences lie. But if you want to know what predicts previous experience, and employment category is one of several other things that you might want to put in your model, then run regression. I just wanted to make it clear that statistically, ANOVA is just regression, but for purely categorical variables. Yes, sir.
In the hypothetically, if you were doing a regression and it just happened that it was just the categorical predictor that was significant, you were running ANOVA after that to see if you were interested.
Yeah, sure. Totally. That would be a great follow-up. Right, because actually this is the only thing, let me dig into this one thing more, and ANOVA would give you a little more, the means and all the pairwise differences. Cool, there's another example for you to look at on your own. This is a housing example. It goes through the full equation and then it goes crafting the equations for each group. We're gonna look at the demo. I'm gonna clear out all this ridiculousness. We'll do the first one and then, oh, I really want to do the second one. It's fun. Maybe we'll do it during review. What?
That one instead.
Cause it's a play around one, you know, but we have time to do it during review, I think. And their DAs more run this model versus this. A cognitive psych example. A cognitive psychologist is interested in what predicts reading comprehension in children. Flex the following variables: vocabulary, attention ability, spatial ability, and SES, low, middle, high. Based on previous research, we expect vocabulary, attention, and SES to predict reading comprehension. Spatial ability should not predict reading comprehension. The study included 2 measures of attention, selective and sustained. It's unclear whether both measures of attention are important for reading. I'm going to start by drawing the model. Everybody should just do this on their paper, but I shouldn't have to tell you that. This is urban exploratory, because we're gonna layer in things piece by piece. Model. I don't worry about drawing them perfectly, correctly, with squares, circles, blah, 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 blah. These are not for reporting. These are for keeping my brain organized. They're very different than when I'm making a figure for a text. One second, back to meeting. Look at this. Can you see that, guys? You can see it. Online, can you see that?
No.
I can see it on my screen.
I can see it.
It's literally just the 4 predictors on the left, 4 arrows, and the outcome. Just a simple theoretical model. The first thing I'm going to do is I'm going to read in the data. It's called ABCD. Looks like this. ID, pick, vocab, flanker, card, picture, reading, list, ew. Those are horrible names. They are names of how they measured those or tasks. So the first thing I'm going to do is I'm going to rename those columns so they make sense to me. We're going to use the function rename from the package dplyr, one of my favorite functions out there. Watch how I do it. I'm going to create the same data set, abcd.dat. I'm going to take the current data set, abc.dat, and then, that's my pipe text, I'm going to rename. New name replaces old name. And then rename, new name replaces old name. If you are not who takes notes on your R script, you're going to go back to your R script and go, shit, which one goes first, new name or old name? That's a note to take. Put new name first and then old name. You don't forget. Once I run that, nothing's going to happen because I renamed it the same data set, but they're all going to be nice names that make a lot more sense to me. Okay, we've got vocab, attention selective, attention sustained, spatial, reading comp, and SES. Now, what's gonna be the issue? What do I have to do with SES to run a multiple regression model? Dummy code it. How many levels does it have? 3. I don't know why I keep working with ones with 3. That's not always gonna happen. If it has 3 dummy codes, then how many dummy coded variables am I going to create? 2. Good. If I have D1, D2, let's make the reference group. What group do we make the reference group? Who has the code? We made low. If the reference group is low, what are they gonna get? 0, 0. Mid is gonna get 1, 0, and high is gonna get what? 0, 1. Good. Great. How do we do it? Well, the first thing is we don't have those dummy code variables. We need to make them. How do I make a variable? Well, I put the data frame name, $, which means variable, and I type the new name that I want to call it. In this case, I called it SESD1. And then I have to tell R what goes in to SESD1. I'm saying, hey R, inside SESD1, I want you to look at the column SES. And if it says low, I want you to make it a 0. If it says mid, I want you to make it a 1. And if it says high, I want you to make it a 0. Then I want you to create another one that's D2, SES.D2. If it's low, I want you to make it a 0 again. If it's mid, I want you to make it a 0. And if it's high, I want you to make it a 1. Once we run this, we're going to have these 2 dummy coded variables on the end that represent collectively SES, with low SES serving as our reference group. We can run descriptives by themselves to check our skew, our kurtosis, our data in general looks pretty beautiful, probably because I simulated it, okay? Our means, and we can run it by SES. Why would we do that? Because you're interested. Good. What's the one I'm most interested in? Probably. Which of these 4 graphs? Reading comp. That's your outcome. I'm trying to know how to predict reading comprehension. And I think SES might be a predictor. Here's reading. Kind of hard to tell just from SES. But here it is broken up by SES. Is this a step you have to check off your process? No. This is get to know your data because you're intrinsically motivated by this research question. You got to dig into your data a little bit. All right, now we're going to look at scatter plot. Am I going to create a scatter plot for my dummy codes? What's it going to look if I do? 2 dots. Good, but I am going to create it between vocab, selective attention, sustained attention, and spatial ability, and reading. Okay? Here they are. Here's vocab and reading comp, definitely linear, positive. Selective attention, linear, positive, but definitely heavy on higher values of selective attention. Where else is that going to show up? The residual plot, because you've got lots of clustered data around the line in the higher values, i.e. less error, and a lot of widespread of minimum values over here on the left. Okay, not bad here. Although this was that other pattern Ali was talking about the other day where the minimal error is in the middle and then it spreads out at the end, but hourglass shape. And then this looks beautiful. Spatial ability, not a great relationship between spatial ability and reading comp, but we hypothesized that. But the error is pretty consistent. We can run a correlation table. I'm going to remove ID and I'm going to remove the dummy code because I don't run correlations on dummy codes. And what I can see is if I look across here, which is reading comp, vocab, significantly correlated. Selective attention, significantly correlated. Sustained attention, significantly correlated. Spatial, not. That's what we expected. Okay? Have you really this crazy visualization? It's a lot. Actually, the individual plots, to be honest, I always run this one as my homoscedasticity error 1. We're going to look for homoscedasticity across the model. One really important thing, when I specify my model, do you see this? LM, linear model, reading, regressed on all of my predictors. That has my D1 and D2 in it. Why? Because that's part of my model. They're not appropriate for correlations or scatter plots, but they are part of my model. They go in here. I'm going to go ahead and visualize my error. And then I'm going to test whether there's a significant relationship between my predictor values and the amount of model error. What do we think visually?
Scholastic?
I think, but kind of hard to tell, but I would say almost scholastic. This model, reminder, what's the null hypothesis? I've asked this every time. We should have this by now. What's the null hypothesis in the Bruce-Pagan test?
No significant difference between predictor variables and error.
Close, not no significant difference.
There's no relationship between.
There you go. It's a chi-square. You've run, it's a chi-square. There's no relationship between predictor values and model error. We want to retain the null. We want basically, it's if I know that all of your values are high and all of your values are low, I do not want to be able to predict the model's performance on you by knowing that. It should be the same. If I can be, oh, well, you have low values, the model works really well for you. You have high values, the model doesn't work as well for you. That means there's a relationship between predictor values and model error. That's heteroscedastic data. We don't want a model to work differently depending on what we put into it. Think about a machine. A model is a function, a machine. You put in inputs, you get out outputs. Inputs are your predictors. What's your output? Your predicted value on your outcome. Wouldn't it suck if your model worked, your machine changed depending on what you put in? That would be heteroscedastic data. Okay. But we're good. All right, here's our data. This one's uncentered. Okay. I'm running it here because I want to use it in the next chunk and I don't want to center all my data. Our outcome is reading. Remember what goes in covariates? Everything we want to use or might want to use. You don't get penalized if you don't use them. It's just everything I might want to use. Now, I'm going to add things one at a time. Now, we're not getting into the decision making now about how we add them, but I will tell you, or you can tell me actually, 2 questions. Why did I add D1 and D2 together? We have to. Why? Same construct, 2 variables. 1 construct, 2 variables. I feel like that's 1 blank, 2 blank. That's like gotta be weird dating website motto. 1 construct, 2 variables. And why would I want to run this first? They all are. It's not my question of interest. I want to know the whole thing. But why did I run this first? It kind of goes to the original question.
See how much variance.
I want to see how much variance is just explained by these 2 by themselves.
So if you run this last, it doesn't explain. I didn't want, if you place this anywhere, but I think the first 2, it doesn't explain.
Well, hold on.
Okay.
Don't
Wait.
talk about the model you already ran before I ran it.
No,
Hold
no,
on. Hold on. I'm running it first because I want to see how much variance it explains on its own. Yes, every time you change the order of your variables, it will change. We're going to run this first. Then I'm going to add in vocab. Why did I choose vocab? It's the strongest correlator. That's not the only way to choose things, but that's why. Then attention sustained and attention selective. And then I put spatial last. It's not correlated. Shouldn't be correlated. But remember, the point, the order matters. It's not that spatial wouldn't matter in any model. It's that if it might not explain additional variance above and beyond everything first. This might not be the only model we end up running, but for now, this is how we're going to run it. Again, at this point in class, our goal is not being experts in decision-making around model building. It is interpretation and storytelling. I'm telling you which models to run. We've got 5 models. They're all going to be significant. Here are their R-squareds. I'm probably going to go straight here. Oh, this one's kind of fun and interesting. All right. Model 1, which is just SES, explains 11% of the variance in reading comprehension. Thank you. Model 2, which adds in vocabulary, explains 23% of the variance. Is that a significant difference? Yes. Model 1, so model 2 is better than model 1. What if we add in, so let's go here. Here's model 1. These are both significant. You see that? There's a difference between low SES and mid SES. Which one has higher reading comprehension? How do you know? The coefficient's positive. For a 1 unit increase in SES D1, meaning a move from reference group to mid, reading comp goes up by 3.21. Same with D2. For a 1 unit increase from low to high, reading comp goes up by 4.90. What we don't have is a mid to high, but that's not a research question. Now, model 2 was better. When we added in vocabulary, we could explain more variance in reading comp. Vocab was significant. Both SES variables, did they remain significant? What happened? Low to mid is no longer significant. There's no longer a difference in reading comprehension between kids from low SES backgrounds and mid SES backgrounds when you take into account their what? Good. Why? Think about that from out there in the world perspective. What is SES often a predictor of? Your knowledge of vocabulary. We can often predict vocabulary rates. There's a correlation between vocabulary rates and SES, but it's not a hard, fast rule. And vocabulary above and beyond is much more of a predictor than just SES. SES doesn't cause reading comprehension. It's a predictor that has a mediator in the middle, vocabulary, exposure to books, things that actually directly do cause reading comp. If we take into account a kid's vocabulary, then actually we don't see a difference between low and mid SES anymore. That's the story that we have to practice. But we still see a what? Between mid and high. What might explain that? What might that? Not vocabulary, because we're already taking into account vocabulary. What else might explain that? Additional support, tutoring, good. Vocabulary might be the same because we're holding it constant, but maybe it's extra good. Now, in model 3, we added in sustained attention. Oh, thank you. Oh God, I'm just swimming. What happens when you go to bed too? In model 3, where we are, 3. In model 3, we added sustained attention. Did we explain significantly more variance? Yes. Let's go down here. What happened here? Same story with SES. When we take into account a kid's vocabulary and sustained attention, we've still wiped out the low to mid difference, but we have not wiped out the mid to high. Interesting. These innate cognitive abilities are not actually enough to wipe out reading comprehension discrepancies between middle and high income kids. Which, as a researcher, is, ooh, maybe I need environmental factors in this model. Good, versus just cognitive abilities. What happens when we added selective attention though, in model 4? No longer. Which one's better, model 3 or model 4? Good. What about model 4 versus model 5? Good. Do I want to look at it though? And we can see selective attention and spatial, not significant, nor was selective attention significant in model 4. I don't love this idea of the best model. I really don't, because there are many models out there and the best model, I think, communicates, I found it. No, you didn't. But what you do know is that these 3 constructs are meaningful predictors, are now the strongest linear combination of predictors you found that predict reading comprehension from the pool that you had. It doesn't make sense to add the other 2. Good. I had one more thought here. Oh.
In model 5.
In model 5. Same.
That doesn't.
What do you mean?
Never, I'm just saying.
Oh, it never changed.
Changing.
No, it's never changing. You notice that? No matter how many cognitive things we add, even when they're not significant, nothing changes about that difference between mid and high. We can wipe out the difference between low income and middle income, but we can never wipe out the difference between middle income and high income.
Low and high.
Low and high, low and high, thank you. Low is the reference group. We can't wipe out the difference between low and high. That makes more sense, actually. Now, what if we wanted to use our model to predict? Notice I just did the same thing here that I did. Really hard to see on that screen, but it's easy to see on R. I just simplified the equation from model 3 into an equation for each SES level. That is, you should feel comfortable doing with categorical predictors. You should be able to take the whole regression equation and generate, it's in the objectives for today. That's what those objectives are for, to tell you what you should know and be able to do. You should be able to take the whole regression equation and be able to generate the equation for any one of the levels of the categorical variable. What's in the slides, it's here for you to be able to see. Okay. And then I just ran it centered for you to look at. And then I ran it as an ANOVA for you, just to prove again that it's the same. This is a really good example of why you should not cut and paste what I do in the demo. I don't do demos to mirror what you do. I do demos to demonstrate things. My suggestion when you're doing a DA is to do your computer and paper. And you start by writing the research question and drawing the model. And then think for yourself, what's the first thing I want to do as a researcher? I want to look at the data. Go to the demo, pull just the chunk that reads in the data, paste that. What's the next thing I want to do as a researcher? I want to look at the data. What's the chunk that runs descriptives? I'm going to pull that. Then your brain is using R as a tool as opposed to R telling you what to do next. If you copy my whole demo and you go step by step, you aren't thinking about how a researcher needs to think through what to do next. I'm literally telling you, there are instructions that I'll do this next. Don't do that, especially as it gets more complicated. Last thing I want to show you, stop share. A lot of questions came up about what to include in your write-ups. I want to show you, it's in multiple regression. What?
The all together now slide.
No, it's not on this one. I got it. I can find it.
That's a good question.
Yep.
Okay, when we determine the intercept of a center data, when with categorical predictor inside,
Good.
did we say is for the reference group?
When all the continuous predictors are average. Good. Remember that when we center predictors, the intercept becomes the expected Y value when all predictors are average. But do we center dummy codes? No, they stay what? Zeros, which means reference group. When we center, that's the predicted outcome level for in the reference group with average values across the other predictors. This is what needs to go in your results section. This. Do you need a figure? Yes. A model figure with results. Do you need a table? Yes. Descriptive, mean, standard deviation, correlation, and regression. You do not need a model figure for every single model you run in the future. Now, if you are testing two specific models, researcher 1 says this, researcher 2 says this, yes, you should put both models because the reader wants to know what you're testing, which model is better. But in the future, if you run 15 models, you laugh, really common. I ran, I don't know, 42 last night. It's not uncommon. If you're running a ton of models, you might not actually end up, you might play, you know what I mean? And you might not actually end up writing up all of those models, depending on what happens. But yes, if the research question focuses on more than one model, you would put all of the models. Generally, what I do is if you end up running a lot of models and you're comparing in the example we just did in the demo, I would probably include the coefficients for maybe model 1, 2, and 3, but I would probably only draw a figure for the model I ended up interpreting, model 3. Again, what's my litmus test? Don't what? What's the only, if, as you're, do I need to X? What should your answer be? It shouldn't be, let me ask a TA, let me ask Jess. What should your answer be? What? No. Does the reader want it? If I don't include it, do I leave the reader wanting? Why do we include a figure with one beta number on it? Because it's easy as shit to look at and see what happened. You don't have to know anything about regression tables. Look at a figure and be like, I got it. There's a relationship. That's why every reader can look at your manuscript and be like, I get it. Now, if you decide you really hate writing about all the see table 1. Now, if your narrative section has no stats, that probably means you didn't talk anything about what you found. Because you at least have to talk about your betas of the model that this is the answer to my research question. That's a good way to think about which betas to include is not all the betas are going to be pertinent to answering your research question. Are going to be around models you ran along, but a certain set of them are going to be pertinent to answering your question. Those should go in the narrative section. Just betas and Ps. You don't need all of them. The rest of the stuff can go in the table. Cool. All right.
Jess, when we're looking at the collinearity output for multiple regression with categorical variables, you don't look at the tolerance for just the level by level pieces at all. You can't sit there and say, oh, 66% of the variance is otherwise explained.
But you remember that the tolerance of those variables are going to be lower because they are dummy codes of each other. But they're not going to be below 0.2, but they're going to be lower than what you're used to. And that's why we regular dummy code and don't dummy code. Because if you fully dummy code, they'd be a lot lower.
I guess the thing I'm curious about is in the output from R, it'll show you a tolerance for each, each level. Is that?
But they were 0.57, 0.55. They were fine.
No, I understand that, but is that showing you the variance for that level of the variable as explained by the continuous variables and the other variable and the other level?
Remember, this is an important question. What he's asking is when you look, and this is just a good big picture regression, he's saying when you look at these VIF and tolerance levels, this tolerance level 0.57, we ran a model with SESD1 as the outcome and all of these things as predictors. And then we got a variance in this explained by all of these, and we subtracted it from 1 and we got this. Is that super interpretable when our values go from 0 to 1? No. Does R know that? No. This is a predictor. I don't give a shit what your range is or what your values are. It's a number. I don't care. That's the thing. It's the same thing with why we don't center or run scatter plots. R will center it for you. R will run a scatter plot for you. R will run tolerance for you. But you have to know it's not meaningful in the context of a dummy coded variable. It's treating it just any other scale. It's how much variance between 0 and 1 did we explain? But you just skip it. The tolerance of your continuous predictors are much more important. Good question. Who has the tests? They're not in my office. Where is Alyssa? Deja has it. I went to my office to get them this morning for you, and they're not here. What are they? Bring it today. I can hang around for a little bit. If anybody wants to review anything, I'll be here for a little bit. Hold on 1 second. Yes.